Good morning, children. I'm here with the next part of the video lecture on the chapter, that is first chapter of class 12, electric charges and fields. As I told you in the last video class that we will starting the electric field. So here is that topic, electric field. Okay. All of you write this heading. And now, once you've written the heading, start writing the definition. The space of influence. The space of influence of a charge around it. It is called its electric field. So the space of influence of a charge around it is called its electric field. See, what is electric field? Let me explain you. See, suppose a charge is there. Okay, this charge is called source charge because see, it will create its field. And what is field? See, suppose you are bringing another charge. Okay, that another charge is called test charge. Okay, so test charge, suppose you are keeping here. So when you are keeping the test charge here, then it will experience some force due to this. And in the same way, you just take this charge even more away. Again it will feel force, but this time lesser force. So as you will keep on increasing the distance of the test charge from the source charge, the force experienced by the test charge will keep on decreasing. And at a certain distance you will find the force is acting, and if you will take the test charge beyond that, then you will find no force is acting on that charge. Okay, so suppose it is able to apply force on the test charge till 10 centimeters, suppose. Okay, so if it is able to apply force 10 centimeter in this direction till 10 centimeter in this direction, then it will able to apply force on the test charge till 10 centimeter in this direction also, and it will able to apply force on the test charge till 10 centimeter in this direction also, and it will able to apply the force on the test charge till 10 centimeter in this direction also, as well as in this direction front, as well as in the direction inside the board. So what we can do, can we take this as a center and take radius of 10 centimeter and we can draw a sphere. And when we will draw that sphere of 10 centimeter, so whatever space is there in this sphere, because see, sphere is a three-dimensional geometry. So whatever space is there in the sphere, this space is called space of influence of this charge. Because if any charge is entering in this sphere, then it is going to apply force on that. If the charge is outside the sphere, it will not able to apply the force. So we can say its influence is limited in the sphere. Okay, in the space within this sphere. Okay, so that is called its space of influence. Okay, now let me tell you, we know that according to Coulomb's law, K Q1 Q2 upon R square. Now see, when the force is going to become 0, obviously when R tends to infinity. So when the distance is infinite only, then the force becomes 0. So this electric field, the space of influence, it is not limited up to a finite distance, but it is up to a infinite distance, because force never becomes 0 unless the distance becomes infinite. That means it acts up to a very, very long distance, although the magnitude of force keeps on decreasing and becomes very negligible, but then also it doesn't become 0. Okay, and that's why field is extended till infinity. Okay, so this you written the definition, I think you have understood also. Okay, it is a actually qualitative thing, not quantitative, qualitative thing is there, quality is there. Okay, charges create their field so that they can exert force. Okay, electric field they produce so that they can exert force on the other charges or uncharged bodies. Okay, because charged body can apply force on another charged body or an uncharged body, both. In this, as you have studied in class 11, no, gravitational field was created by the masses. Okay, in the same way the charges create electric field. Okay, so the next heading is electric field intensity. Okay, now see how it is defined. It is defined as electric field intensity at a point. Where we are going to define? At a point. And where that point is situated? In an electric field. That point is situated in an electric field. Okay, because if you want to find out electric field intensity, obviously it can be found out at any point. Okay, but that point should be within the field, because outside field, how we can have a electric field intensity? We cannot have. Okay, we can have electric field intensity at the points within the field only. Okay, so defined as the amount of force that is equal to the amount of force. Which force? Force which is experienced by a unit positive charge, because unit positive charge is taken as a standard here, or we can say by convention we take unit positive charge. Okay, and it is placed at that point. Okay, so at whatever point in the field you want to find out electric field intensity, you have to place a unit positive charge, and whatever force that unit positive charge experiences due to that field is called strength of the field at that point. Okay, so please note down this definition first. Okay, once you have noted down this definition, see, it is a vector quantity. It is a vector quantity. Okay, denoted by vector E. Okay, and has SI unit. Newton per coulomb. Okay. Newton per coulomb or volt per meter or joule per coulomb meter. Joule per coulomb meter. Okay, these are the units of electric field intensity. Okay, which is denoted by vector capital E. It is a vector quantity. Okay, see, it is point dependent. Okay, see this electric field intensity, suppose there is a charge Q, this is source charge obviously, and it has created its field. Now if we will place the unit positive charge here, suppose, okay, what will happen? It will experience some force due to this source charge. Let that force is F1. Now if you place that test charge here, again it will experience some force due to this source charge. Let that force is F2. When you place this test charge here, again this test charge will feel some force due to this source charge. Let this force is F3. What do you think? Will all these forces will be equal? No, not at all. Obviously F1 will be greater than F2 and F2 will be greater than F3. So that means as we change the points, the value of forces change. Why? The same charge placed in the same field experiencing different force, because strength of the field is different at different point. Okay, or we can say the electric field intensity is different at different point. Here it is experiencing more force because electric field intensity is more at the points which are nearer to this charge, and it is lesser at the points which are away from this charge, that is source charge. Okay, so as we move away from the source charge, the electric field intensity becomes lesser and lesser. Okay, so it decreases. Now, according to the definition, no, suppose you are keeping here a charge, suppose q naught. Okay, now how much force, and this distance from this charge q, this distance is r. So how much force this q naught charge will experience? According to Coulomb's law, we can calculate that. Okay, and that force will be how much? It is F is equals to K q naught upon r square. Okay, so from here we can say that when we are keeping their q naught charge, then it is experiencing how much force? F force. So when we will place their unit positive charge, then it will experience how much force? Obviously it will experience F by q naught force. And according to definition, whatever force that unit charge is experiencing, that is equal to, numerically equal to electric field intensity at that point. So electric field intensity, suppose this point is P, at point P is how much? Electric field intensity is F upon q naught. Okay, this formula we get from here. Now you know the expression for F, so you can write from here E is equals to K capital Q naught upon R square, and here this Q naught is also there. So this Q naught and this Q naught will cancel out, and we are left with E is equals to K capital Q upon R square. So this is the expression for electric field intensity. See, only source charge is appearing. Okay, and the distance of the point from the source charge. Okay, so this is the expression for electric field intensity. Now you can write in vector form because it is a vector quantity. So in vector form, what you can write? E is equals to F on q naught. Okay, so electric field will be directed along the direction of force provided the charge is positive. Okay, if the charge is negative, then obviously electric field and force will have opposite direction. You can see from here. Now one more thing, as electric field intensity is also given by K capital Q upon R square. Now see, for free space, what we can write? E is equals to 1 by 4 pi epsilon naught Q upon R square. For medium M of permittivity, rather not permittivity, we can write, okay, permittivity epsilon. What will happen? E is equals to 1 by 4 pi epsilon not, I'm not writing not at all, okay, upon R square. But you know that this can be also written as 1 by 4 pi epsilon naught epsilon R, that is relative permittivity. Okay, Q upon R square. Okay, in this way also we can represent it, write it. Okay, so these are the formulas for electric field intensity in different situations. When the medium between the point of observation and the source charge is air or vacuum, then it is called free space, then we can use this formula. And when the medium, this medium between the source charge and this point is some other medium having permittivity epsilon, like it is not air or vacuum, suppose it is water, this charge is placed in water, or this charge placed in kerosene, or this charge is embedded in asbestos, then whatever permittivity of that medium is there, that will be reflected over here. Or you can use its relative permittivity, and you can use this formula. Okay, so these are the formulae for to find the electric field intensity. Okay, See, the next topic is principle of superposition. See, already we have done the principle of superposition for force, okay, Coulomb force. Here we are going to study the principle of superposition for the electric field intensity, okay. See, what does it states? First you write the statement, okay. Start writing. It states that the electric field intensity due to a particular charge at a given point remain unaffected due to presence or absence of neighboring charges. That means, suppose here you have got charge Q, and due to this charge Q at this point P, which is at distance R, the electric field intensity is suppose E, or rather E1, okay. No other charge is there, so its electric field intensity at this point is E1. Now suppose at the same time, no, now later on what happened, you brought other charges, suppose Q1, okay, Q2 and Q3, okay. Then also at this point electric field due to this charge will remain same, it will not get changed. That means these charges are not going to affect its electric field intensity at this point, okay. Obviously they will have their own electric fields at this point, but they will not affect the electric field of this charge, okay. Now what does it mean? What conclusion we get from here? How it helps us? What is the need to study this? See, suppose this charge, this charge is Q naught. Suppose it has produced electric field E naught. Suppose this charge has produced here electric field. This charge has produced electric field. Suppose in this direction, and this charge has produced electric field in this direction. Suppose, okay, it is E1. This charge has produced electric field in this direction. Suppose this is E2. Okay, this charge has produced electric field in this direction. Suppose this is E3. Then what will happen? No, we can find these electric fields very easily, because we know we have to find its electric field. We don't have to bother about other charges. While finding the electric field due to this electric field intensity due to Q1, then we don't have to bother about other charges. We have to consider this charge and the distance. That's all. And when we are trying to find out the electric field due to this charge Q2 at this point, we have to bother about this charge and this distance. We don't have to bother about other charges, okay. And if you want to find out net electric field at that point P, so net electric field will be, obviously it will be E naught plus E1 plus E2 plus E3. So you have to take the vector sum of all the electric fields at that point, and so that you can get the net electric field at that point, okay. So in this way you have to take the vector sum of electric fields due to different charges at the given point, and then you will get the net electric field, or you can say total electric field at point P. Remember, it is vector sum, not simple sum, because electric field is a vector quantity, okay. In case of multiple charges, no, suppose there is a charge Q1 which is placed at distance R1 from this origin, that means its position vector is R1. Another charge is there Q2 whose position vector is R2, and there are lots of charges Q3, Q4, Q5 and so on, and at last you are having Qn charge which is whose position vector is Rn, or you can say which is at distance Rn from the origin. In this case, suppose you want to find out the electric field at point O due to all these charges. So first of all, we will find the electric field due to Q1 at O. That electric field is, suppose electric field intensity is E1. Now electric field intensity due to charge Q2 at point O is E2. In the same way, electric field intensity due to charge Q3 at origin is E3. And similarly, similarly, electric field due to charge Qn at origin is En. Now in order to find the net electric field at origin, what we need to do? we have to take the vector sum of all. Okay. Now let us take a question. See, there are two charges Q1, Q2 separated by a distance r, and we need to find out the electric field intensity at point P, which is at distance d from Q2. Okay. So we have to find out the net electric field at point P due to both charges. So we have to take one charge at a time. Let us mark here capital A, let us mark here capital B. Now from A, what is the distance of point P? It is obviously R plus D. So we can write electric field due to charge which is placed at point A will have magnitude how much? K. Obviously the medium is free space. Okay. Q1 upon the distance square, that is R plus D is the total distance. So we have to write its square. Okay. Now in the same way, the electric field intensity due to charge which is placed at B will be K, and charge is Q2 and distance is how much? Only D. So we will write here D square. Okay. Now if we want to find out the net electric field, so we must know the direction of these electric fields. Now see, what direction of electric field is determined by the force experienced by unit positive charge. Suppose you are keeping here unit positive charge, so we have to see that this Q1 charge is applying force on this unit positive charge in which direction. If it is attracting this, if suppose Q1 is negative, then it will attract. So direction of electric field will be there in this direction. If it is positive, then it will repel. So direction of electric field will be in the opposite, that is away direction. Okay. So we need to know the sign of these charges. Okay. And suppose this Q1 is negative and this Q2 is positive, then what will happen? Obviously Q1 will attract this unit positive charge. So this EA will be directed in this direction, rather vector EA, and this Q2 charge, as it is positive, so it will repel this unit positive charge, so it will be directed away, okay, in the direction of repulsion. So what you found, both the electric field intensities are directed opposite to each other. So when we are going to find out the net electric field at point P, what we will get? We will get EA vector sum EB. Okay. And when we are talking about the vector sum, that means we have to consider the direction. As directions are opposite, so one has to be taken negative. Now, which is more? Obviously, EB is more because distance is smaller. Otherwise, but it depends on the charge also. Okay. So we cannot say which is smaller or which is larger here. Now see here. It is your choice which direction you are going to take positive. You are going to take this direction positive or that direction positive. If you are taking that direction positive, then this direction will be taken as negative. So you can write value of EB, that is K Q2 upon D square minus K Q1 upon R plus D whole square. So in this way we can find out the net electric field at point P, and whichever is more, whichever is having more magnitude, it will be directed in that direction. Okay. If suppose EB is more, then this net electric field will be directed along the EB. If EA is more, then it will be directed along the direction of EA. Okay. In this way we used to find out the magnitude and we used to tell the direction. Okay. Let us take another question. This is an equilateral triangle, you can see, having each side A, and A is equals to how much? 1 meter. Okay. And now see, there are two charges. Q1 is minus 10 coulomb and Q2 is how much? Plus 10 coulomb. And Q1 is placed at point B and Q2 is placed at point C. Okay. And what we have to do, we have to find out the net electric field at point A. Okay. So we have to find out net electric field at point A. That is our question. Now see, first let us discuss about the directions. If you want to find out the direction of electric field due to q1 charge here, then you have to place here unit positive charge, that is 1 coulomb positive charge. Now you tell me, this q1 charge is going to attract this charge or repel this charge? Obviously this is negative charge and this is positive, so q1 will try to attract this plus 1 coulomb positive charge. So it will attract in which direction? It will attract in this direction. Okay. Now, so electric field due to this q1 charge, we can say it is E1. It will be directed in this direction. Now, the same plus 1 coulomb charge is placed, plus unit positive charge is placed over at the same point. Now, what this q2 will do with this? It will repel this or attract this. See here, obviously both are positive charges, so it is going to repel. So it will repel in which direction? It will repel it in this direction. It will make it move away from it due to repulsion. So electric field due to charge q2 is E2, is directed in this direction. Okay. So these are the directions of these two electric field intensities produced by two different charges. Now we know that we need to find out the net electric field. Okay. So in order to find net electric field, we can draw a line which is parallel to this base. This is parallel to this. This line is parallel to BC. Now, when it is parallel to BC, you can just see all the angles of a equilateral triangle is how much? It is 60 degree. Now, as this is parallel to this, and suppose this is transversal. If AB is transversal, then this angle will be equal to this angle. Alternate angles. So this is also 60 degree. At the same time, if these two are parallel and this is transversal, AC is transversal, then this angle are corresponding angles. So this will be also 60 degree. Okay. Now we can take the components. We can take component of E2 first. So we know that the side at which angle is connected, that we can write what? We can write E2 cos theta. Angle is there, okay, no problem. That angle is theta, or rather you can write a specific, that is cos 60. And here what you will get? E2 sin 60. Okay. When we are talking about E1, then again you can write angle is connected this side, so we can write E1 cos 60, and this side we can write E1 sin 60. Okay. Now see what will happen. Let us find the magnitude of E1 and E2. E1 is how much? Obviously K. Q is how much? It is 10 upon distance is how much? It is A. But A is how much? 1 meter. So rather we can write A. That will more better. Okay. And what about E2? E2 is again K. Q. Q is how much? It is again 10 upon A square. Remember, the formula for electric field is somewhat like this. K Q upon R square. Okay, remember. Okay. So we need not to take the sign of the charge at all, because sign of the charge is used to find the direction of electric field intensity, and that's why sign is not used in finding the magnitude. Okay. So we will not taking the sign of the charge at all. Okay. Now what you find, both the electric field intensities appear to be equal. So what we can write? Can we write E1 is equals to E2? I am not putting arrow, that means magnitude I am talking about. So is equals to, we can write, let it be, we can write E1 is equals to E2, okay, and that is equals to how much? Value is, it is 10 K upon A square. That's what we can write. Or we put the value of A, that is 1 meter. So what we will get? We will get 10 K only. If we put the value of K also, we can write 9 into 10 to the power 9 into 10. That means we can write 9 into 10 to the power 10. Okay, Newton per coulomb. That's what we can write. Both are equal, so we can write like this. Now, once we have written like this, and both the electric field intensities are equal, so See here, E1 and E2 are equal. Sin 60, sin 60, it is also equal. So the vertical components will balance each other. Okay, so E1 sin 60 will be equal to E2 sin 60. Okay, so vertical components will balance each other. Balance each other. Okay, they will balance each other. Now, so electric field intensity will be there due to only horizontal components. Okay, so the electric field intensity will be there due to horizontal components. Now see, what about horizontal components? Net electric field intensity is E1 cos 60 plus E2 cos 60. That is there. But E1 is equals to E2. So what we can write? If E1 is equals to E2, then either you can replace E2 by E1 or you can replace E1 by E2. Okay. Suppose I am going to replace E2 by E1. So what we will get? E1 cos 60 plus E1 cos 60. Like this, E1 cos 60 plus E1 cos 60. That means we will get 2 E1 cos 60. But what is cos 60? Cos 60 is 1 by 2. So 2 cancels out. We will have E1. What is the value of E1? It is 9 into 10 to the power 10 Newton per coulomb. So this is the net electric field. Okay, which is obtained at point A. Now what about its direction? See, it is directed along this. So we can say it is directed parallel to CB. Okay, so we can write the direction also. It is directed parallel to CB. Okay, it is parallel to CB. That's all. Okay, okay, that's all for this video. In the next video we'll discuss about the electric field lines, okay, and their pattern. So remain safe, remain isolated from each other, and be healthy. Thank you.